It's time for Math with Mr. Troy. It's time for Math with Mr. Troy. It's time for Math with Mr. Troy. Okay, so we are going to see how you can use matrices to solve systems of equations. And the first thing we're going to talk about is how you take a system of equations and you write it into a matrix. So I want you to look at the 3x3 system at the bottom of the screen and notice how the coefficients are in the same order and the constants are in the same order. And the only difference is that there are no blank entries in the matrix. So take a look at our bottom line. We have 2 x's, we have 0 y's, and -4 for z. This line right here is called a partition, and sometimes that's written as a solid line, sometimes that's written as a dotted line. Here you can think of that like an equal sign. You can contrast this with a matrix equation, which is going to represent all of the same information, but is going to be about halfway in between for the amount of writing that you have to do. This, which we'll see later, is called an augmented matrix here on the right side. That is going to be the least type of writing, and that's going to be what we're going to look at today. Okay, so we're going to jump right in, and we are going to solve this system using Gaussian elimination with back substitution. And you will see that this works exactly the same way that we did with systems before, just with less writing. So I'm going to start by eliminating these 2 positions. When I eliminate them, instead of them just disappearing, we'll have a coefficient of 0. So I'm going to do row 2 plus row 1 and store that in row 2. And I'm going to do row 3. The numbers in row 2 are slightly smaller, so I'm going to say plus 2 row 2 and make that my new row 3. So I have a choice there. I chose to use row 2 instead of row 1 because the numbers are slightly smaller. So this process works exactly the same way. The only added wrinkle is that I now have a new column to keep track of. At any time, you can stop and say to yourself, okay, what does, say, the bottom row mean? Well, it means that 6x minus 6y equals 0. So the next thing I'm going to do is I'm going to multiply that bottom row by a scalar of 1/6. I know I could cancel it out right now, but I want to kind of show what incremental work looks like. Another thing I did was I multiplied the middle row, row 2, by -1 so that I could start to get that nice stair-step pattern. Okay, so you can see I've got 1s on my main diagonal. I do still have this pesky 1 right here. So I'm going to take row 3 and I'm going to add -1 row 2 and put that in row 3. Okay, at this step I am in what is called row echelon form. Now, I know we've talked about this before, but just as a reminder, that means that each row starts with a 1 and that every 1 has a 0 underneath it if it has a row underneath it. At this point, because we're doing Gaussian elimination with back substitution, we've just shown that z equals 2. So we can take our second row out, which is y minus 2z equals -2. And that gives me that y equals 2 as well. Then I go up to my top equation, x minus 4y plus 3z equals 5. And I can simplify and solve, and I get x equals 7. So my solution is 7, 2, 2. This is a pretty nice and clean way to solve a system. You work matrices until you're in row echelon form. All ones on the main diagonal, zeros underneath. And then from there, you do back substitution. So plug z into the second row and find y. Plug y and z into the first row and find x. A reminder on some of the terminology on that matrix. If you take the original system and write it with the constants or with the totals, that is called an augmented matrix. The word augment means to make bigger, so an augmented matrix, whereas everything but the totals would be called the coefficient matrix. When we were solving using inverse matrices, that was our A, which we then found A inverse for. So as a reminder, that method is called Gaussian elimination with back substitution. And the next method, a twist on that, is called Gauss-Jordan elimination. It takes the steps further still inside the matrix. So the first thing we do is we write our system into an augmented matrix. I've done that. When you're doing this, you want to be really careful to make sure you don't drop any negative signs or to make sure you don't just randomly write any of the wrong numbers. A really simple mistake that could really ruin your day. I'm going to solve this one pretty similarly to the way that I did the last one. I'm going to take row 2 and I'm going to add it to row 1, and that's going to cancel out, or I should say eliminate, that negative 1 here. And then I'm going to use row 2 again, and I'm going to eliminate this 2 here. Okay, so here's my work from that. You want to be really careful, check your work, make sure you write down what you're doing, otherwise you can be really confused. It's always better to double check than to do the entire problem twice. The next thing I'm going to do is I'm going to eliminate the y's in the bottom equation. And then I'm going to make sure that I have 1z. So I'm going to multiply this bottom row by 1/3. I know these steps are pretty quick and I'm just saying what I'm doing and not working through the arithmetic. Go through and make sure you have a fair understanding of what's going on here. Okay, to make sure I'm hammering home the difference here, we have reached a row echelon form. Now, many things can be row echelon form. They just have to have one with zeros underneath it, one with zeros underneath it. It doesn't matter what this number is or what that number is or so on and so forth. If that's where you're ending, that's just Gaussian elimination. If you take it further and you go to reduced row echelon form, then you're doing what's called Gauss-Jordan elimination. Okay, so let's take this onto another page, and instead of doing back substitution here, let's continue to work inside the matrix. So the benefit of finding z first is that it makes it quite easy to eliminate z from the above rows. So now I can do row 2 plus -4 row 3. And that's going to get rid of the z's and therefore just leave me with y. The fact that I already turned this into a 1 makes that step even easier. In row 1, I can add -3 row 3. And while I will still have some y's in there, that'll be okay because I'll be isolating y in the second row. So there's that work. And now I can just add row 1 plus 2 row 2, and that will cancel out the y's in the top row. So if we go this far, we have reached reduced row echelon form. There is only one reduced row echelon form because I have reached the identity matrix here. There's no way to make that more simple. And this tells us that our solution is 1, -1, 2. Sometimes when you're solving matrices, you'll see people give their answers like this. And you would see how that's kind of the same thing as what we've got here. All right, everybody, I hope that video was helpful. That's Gaussian elimination and Gauss-Jordan elimination. I think I just said I hope that video was helpful. Well, I hope it was helpful, but I also hope it was helpful. All right, that's been one more day of math with Mr. Troy.